I'd like to invite Dr. Aprajita Verma, who is coming to us from Oxford University, who's going to talk us through a new area in astronomy, the Vera C. Rubin Observatory.
Thank you very much, Jane. Can you hear me okay? So thank you very much for inviting me to speak about this really incredible facility that we're about to start observing with. Although this is clearly on the ground, I am by my previous incarnation, that's not the right word, but in my history, a space telescope scientist. So I've worked with, going back all the way to IRAS, for those of you that worked on that, the Infrared Space Observatory and the Herschel Space Observatory, and also now working with Euclid. There's a lot of synergies in this current time of kind of fundamental and really quite impressive facilities that require huge collaborations to realize, and the synergy between space and ground we're really in the era where that really gets maximized through things like the JWST, the James Webb Space Telescope. So I'm going to talk mostly about the Vera C. Rubin Observatory, and it really will revolutionize our understanding of the cosmos. There's a picture of this here. It's located in Chile, in the Atacama Desert. You see a picture of Cerro Pachón there, where the facility is being built. It's jointly funded by the US National Science Foundation and the Department of Energy. This is the first ground-based astronomy facility that the DOE has funded. But I also wanted to draw your attention to, oh, sorry, is there a pointer on here? The top. Okay. Well, I'll just, this box at the bottom, there are about 29 countries providing international contributions in kind to this incredible facility. And the UK is one of those who are a major partner. We'll be reprocessing up at Edinburgh 1/4 of the data that comes off this telescope. And that's funded through the UKRI STFC. And the consortium basically includes every astronomy department in the UK. It's currently called LSST UK. And I manage the International In-Kind program at Oxford for the whole observatory. So what is the crux of this facility is this giant camera. So you're looking at it kind of face on. You see in the center there, the actual focal plane, which is enormous. You can see the moon on this blowout there for scale. And basically, it's a 3.5-degree field of view. It's the largest camera ever made with 3 billion pixels. So this is really state of the art. It's really incredible and is optimized to map as much of the sky as we can possibly do in 6 filters from the UV to the infrared. This is the filter camera, so I'm quite short, but I'm basically the height of that filter mechanism there. Just to give you a feeling of the scale. So what the mission of the whole telescope is to capture the cosmos. So you've already seen the camera. There you can see taller people than me next to the camera, but again gives you an idea of the scale of this thing. On the previous slide, it really does just look like your kind of zoom lens on your SLR, but just really hugely magnified. We need a telescope that is very innovative and is optimized for speed. So as you can see here, this is the structure of the main telescope, the Simone telescope. It has an 8-meter mirror, which is currently amongst the largest ground-based mirrors in existence. It will be superseded by the extremely large telescopes that are 40 meters across, that are still some years off, but hopefully within the next few years. But this one is very different. It's very squat. It has a very high F ratio. It is really designed to slew very quickly across the sky to map the sky as quickly as possible. And by doing so, we also want to see very faint objects in the universe. So essentially, these three ingredients basically allow Rubin to map huge swathes of the sky very, very quickly. So in one night, or every 3 nights, they can cover the whole southern sky visible to it, a third of the sky every night. So this is what we call the legacy survey of space and time. So that is the survey that the Rubin Observatory will be doing. And basically, it will be repeating that scan of the sky, so revisiting the same patches every 3 nights for 10 years. And this is really the first ever movie of the universe in high definition and with great image quality. Okay, so I've already mentioned, so it scans the night.
The universe is a dynamic place, but how do scientists spot changes in the cosmos? First, they need...
I thought I had switched off all audio, but clearly...
To know what...
Thank you. Although he'd be very interesting, probably more interesting than I am, to be fair. But okay, can I go back to that slide? So can I still play it with? Yeah. Okay. So because we have this kind of the first time we have real-time information, we're actually able to really make this movie of the sky and learn a huge amount more about transient or moving objects in the universe. So the things that you see listed here in green are things that move, explode, change their brightness. So we'll see variable stars, asteroids and comets, pulsating stars, supernova explosions. And then on top of that, we have still the static universe that we're kind of used to. So it will reveal more stars and galaxies. We'll be able to really look at very low surface brightness features that I'll mention in a little while. But also there'll be lots of unexpected discoveries. So these are the kind of 4 science pillars of the Rubin telescope. So I'll just go through these quickly, but one of the key ones is really mapping the Milky Way. So with current facilities, you can do this, but it takes years to achieve what Rubin can do in days. So we can map the whole Milky Way, we can look at the things falling into the Milky Way, we can look at our local neighbors, and really make an inventory of structure and content around the Milky Way. Similarly, in the solar system, again, it's very hard without huge area and depth to really understand or really catalogue or make an inventory of the solar system. And this is another thing that Rubin will do. And again, because of the time domain aspect, we can really see the things that move. So that links into the changing sky, and I spoke also about the transients and asteroids. And all those transient things, all those static things, all feed into also our understanding of cosmology. So we really want to understand kind of the fabric of the universe, look at issues like dark matter, constrained dark energy, which is the acceleration of the universe. And Rubin, because of its sheer size, will allow us to have multiple probes to trace not only dark matter, but also dark energy. And so these are all kind of really hot topics in astronomy and cosmology at the moment. And it just kind of demonstrates the versatility of Rubin, that it really has the capacity to provide answers in many areas of open questions in astrophysics and cosmology. So it's obviously named after Vera Rubin, and kind of the dark matter aspect is a lot of the reason why. Vera Rubin was an astronomer who lived in 1928 and sadly passed away in 2016. But she really provided the first observational evidence of the existence of dark matter around galaxies. And this is the first observatory, or the first major US observatory or facility that's been named after a female scientist, and a hugely impactful and pioneering one at that. So I'm going to now kind of switch to just showing you some pretty pictures, basically. So Rubin hasn't yet started the legacy survey of space and time. We're hoping to start that formally this month. But they did release a first batch of data. So what you see here is basically about 7 days worth of data. And I hope you find them as impressive as I do. So this is a Trifid nebula, and basically this is about just a little bit larger than one Rubin footprint. But what I'd like to draw your attention to is the huge dynamic range in this image. Also, all those little tiny dots you see are individual stars. Mapping this area would take, again, years. But again, this is something Rubin can do in a matter of an hour. And you can see also kind of that low surface brightness structure. So this is really just incredible science that we're just getting really through the end of commissioning of the camera. So it's really quite remarkable. And again, in 7 days we can do this. You can imagine, or I can't actually, what we can do in 10 years. On the other scale, so moving away from the galaxy to the extragalactic universe, this is what they call the cosmic treasure trove. And here you can see just a patch of sky that contains kind of our usual familiar elliptical galaxies, disk galaxies, a couple of stars. But you see kind of nice features. Again, you can see these kind of low surface brightness halos that show in this region. Kind of in the top left there, you can see things that are interacting, so galaxies that are basically interacting with each other and creating kind of stellar halos around them from the results of that tidal interaction. You see a couple of gorgeous disk galaxies there. But again, this is a zoom in, and if we just kept going, you just see more and more stuff. And I'll show a link on the next slide if you want to explore any of these images. But again, you just see the enormity of this data. So this image, the one that's in the background, contains about 10 million galaxies. That's 0.05% of all the galaxies that Rubin will see in its lifetime. So again, we're just inundated with data. So I mentioned this Sky Viewer app. So if you go to rubinobservatory.org, you can play around with these images, you can zoom in. But one thing that I wanted to bring to your attention here is, can you see these multicolor streaks? Okay, so these are basically stacked images. So you're taking those images that you're taking repeatedly over the sky. Rubin does 15-second or 30-second exposures. So as you make these stacks, things that move change in color because you're taking it with different filters. So each of these tracks actually represents a moving object, which you may have seen recently in the press. Hopefully this will start without sound. But basically, we're just going to watch a movie of things that we know that don't move versus new things that do. So basically, again, within these 7 days, Rubin discovered about 2,100 new asteroids. And so you see these all clearly popping out in that stacked data. And this is basically nothing, right? We get 10 million changing objects every single night. Now, that can be in brightness or in motion. But again, you're just seeing the enormity and the potential of this incredible data set. So this is, again, something that we've never been able to do, right? And so here you can see how that relates to our local universe, or the local solar system, and really mapping that out over the whole sky that's available to Rubin will be an incredible resource. So the thing that I mentioned at the end that's kind of hard for any of you who are in research council funding bodies, this is the hardest sell, perhaps. But it's the most science-worthy part of any new facility. When we're pushing the boundaries of scale and size and technology, really the key that comes back is the stuff we can't predict. So we know we're going to find things that we don't understand. we know we're probing a range of kind of variability that's never been probed before, 15-second timescales of variation, right through to 10 years. This is a whole new domain. We're going to find out so much about the universe and not be able to answer those questions, yet drive that science curiosity forward. So I will just quickly mention that the Rubin data is designed to be for everyone. While we'll have kind of internal data releases, eventually all that data will become public. We have an integrated education and public outreach program, and I forgot to actually acknowledge the EPO team who generated these slides. I can't take any credit for them. But again, we have like a three-pronged approach: education, outreach, as well as citizen science. And there are already citizen science projects available on the Zooniverse platform, should you wish to contribute to Rubin science. So I'll just end with a quote from Vera Rubin. So don't shoot for the stars. We know what's there. Shoot for the space in between. And that's where the mystery lies. Thank you very much.
It's just overwhelming. I don't think I'm the only person that when you started showing those movies, I got goosebumps.
Oh, wow. Amazing.
So big thank you. Do we have questions in the room? Yes, absolutely.
Thank you for that. I met Vera Rubin when I was a student years ago, and I was tremendously impressed with her, and it's great to see this telescope named after her. Well deserved. You mentioned a little bit about the data release. Can you say anything about the timing of when data will be more generally available?
Yeah, so basically we get, as data comes off, it gets processed, but there'll be a period where that's kind of frozen so that we do a uniform processing. And that will be kind of 1 year after it's taken, roughly. So we're expecting kind of the first batch of, let's say, more data than what I've just shown you that comes from the early phase, already kind of towards the end of the summer in 2026. But the official first release will be sometime in 2027, but that will be internal. 2 years later, it becomes fully public. But there will be publicly available parts of that, either in the citizen science projects or things that we share on the observatory site. So it's not that we hold the data; it's just to make sure that we've got kind of the data in a good state before it becomes publicly available.
Yeah, sure. Thank you.
Oh, and sorry, I should have said then there are annual releases after that.
Thank you very much for that. That's so exciting. Could I just ask you about spectroscopy? I think you mentioned 6 filters, is that right? And is that basically the approach for spectroscopy? Yeah, so obviously spectroscopy takes a lot longer to collect the photons. So a proxy for doing spectroscopy is to use multiband filters. And we can kind of build up a spectral energy distribution rather than a spectrum and learn things about the objects that we're doing. But coupled to that, there are other ground-based facilities and space-based facilities that have spectroscopy capability. So you can see Rubin as feeding targets to those spectroscopy missions or telescopes. And actually what we can do is just look at a subset of a particular type of celestial object and kind of get a representative understanding of what the spectra would tell us for that type of object. So because spectroscopy is so expensive in terms of observing time, that's the kind of approach that we do. We use the kind of smaller subsample to get the good spectroscopy, and then coupled with this photometric information we get from the multiple bands, we can kind of calibrate what the photometry is telling us. Yeah, presumably you can do crude spectroscopy with
but very crude. We're looking at R of, I don't know, 50 or less. Yeah.
Okay, thank you very much. We thank Dr. Verma again. And